Welcome. In this video, we wanted to carry out some supplemental discussion, in particular about how Bohr's postulate of the atom, in particular that the momentum was quantized, how that could be justified. So just a quick recap. Remember, Bohr's predictions were that the electron orbits, certain electron orbits are allowed, and they are given by this formula. This formula he obtained by assuming or by postulating that the angular momentum of an electron is quantized. And this is what that reduced to. This is angular momentum on the left, and this is the quanta of the angular momentum. The key point here is that n is an integer, that is a positive integer. It's a number that assumes values of 1, 2, 3, 4. And this 2 pi, h over 2 pi, is also a constant. So this means momentum, angular momentum, comes in multiples, integer multiples of h over 2 pi. By us making this assumption, he was able to determine which regions electrons were allowed to orbit in. But why was this? Why did this work? We still don't have an intuitive idea as to why did this kind of an assumption, kind of a postulate, allow Bohr to do this. Is there a fundamental truth to it, or was it just a desperate move? Well, let's talk about it a little more. A quick recap about photons, because photons are essentially an example of X-rays. X-rays are photons are quanta of electromagnetic radiation, and photons have particle and wave properties. Photons also are massless. Because they are massless, one might think their momentum must be zero, because by definition momentum is equals to the momentum P is equals to mass of that photon times v, the speed of the photon. But if the mass is zero, you might assume the momentum of a photon is zero. However, that is not true. The actual photon momentum is given by this formula. This is the momentum is equals to h, the Planck's constant, divided by the wavelength of that photon. The point here is that a photon wavelength, in other words, a photon with a wavelength, lambda n, has a momentum given by p sub n. That is quite important. And if you're interested in understanding where this formula comes from, I have a slide here which I'll quickly discuss. And that is the energy of relativistic particles, that is particles that are moving very close to the speed of light. And they have mass, and they are not under any influence of any force. The total energy of those particles is given by this formula. That is, the energy squared is equals to the momentum squared times the speed of light squared times the mass of that particle squared times the speed of light, this time raised to the power 4. However, we know photons are massless. So this means m here is going to be 0, which means this term is going to disappear. What we are left with is E squared is equals to P squared C squared. Take the square root of that on both sides. What we end up with is the energy of a photon is equal to P times C. But remember, we knew from earlier on that the energy of a photon is given, we know that it is equal to h times c time divided by lambda. This formula came from this old formula that that energy is equals to h times the frequency. These two formulas, this and that formula, these are the same thing essentially. Well, the point is here, if we take this energy equation and equate it to Pc, we can deduce that the momentum of a photon is actually indeed h over lambda, just as I had declared here. So you don't need to know this. This is just background info so you understand where this formula comes from. It doesn't just descend out of the sky. Well, now that we know that the photon has momentum given by h over lambda, we need to discuss a principle which was proposed by de Broglie, a French mathematician and philosopher. His observation and his proposal or principle was that, well, the idea that particles have momentum and wavelength should not only be considered to be a property only of photons. He rather thought of all particles which have momentum, that these particles, if they have momentum, we can associate a wavelength to them. Any particle. It could be massive, it could be massless. If that particle has non-zero momentum, we can associate a wavelength to it. And in this, he introduced the idea of what we call matter waves. In other words, even physical matter, not only photons, but even every particle in the universe, we can think of it as being a wave. In other words, every particle has a wave nature, which we describe as matter wave. So that wave nature is not only a property of massless particles, but an electron is an example of a particle that has momentum. Therefore, because the electron has mass me, when the electron is moving at a speed v, its momentum is given by P is equals to MEV. M sub E times V. Which means to this electron we can associate a wavelength. All I've done is I've taken this formula for momentum, which we saw with the photons. I've just reshuffled it and I've substituted that P is equals to MEV, and that's why we have this. This means if we can treat electrons as waves, if an electron has this momentum, we can treat it as a wave which has this wavelength. This is critical for us to appreciate. If there are any questions, post them in a comment section, but this is the jump. If you have a particle that has a momentum, that particle can be treated as a wave with this wavelength, with this matter wavelength, which means we can treat electrons as waves. But waves have other principles that they obey. In particular, the first principle that waves obey is the principle of superposition. All this means is that when two waves come and combine, their effect is always additive. In other words, waves will interfere either constructively or destructively. They will interact or interfere constructively wherever their amplitudes line up. But whenever their amplitudes are out of phase, they will interfere destructively. But remember, electrons can now be treated as waves. This means electrons will also obey this property. They will also constructively interfere and destructively interfere depending on the conditions. Therefore, electrons will not be observed in any region where they destructively interfere. This is setting the stage for why electrons occupy certain orbits and not others. The reason why we don't observe electrons in certain orbits, it's because in those orbits they would have interfered destructively, hence they would have negated one another. That's why we never observe them in that region. But in the region where they constructively interfere, we will observe them. Hence that becomes the allowed region that the electrons can occupy. Over here I have a picture. This picture is not a picture of an electron, it's just of a random wave. So imagine a string. The string is pinned on two ends and it's sent to vibrate. So obviously this string has many waves vibrating, propagating through it. But you will notice that there's points where there is no vibration. These points here are where the waves on the string are destructively interfering. In these nodes, sometimes we call them nodes, especially in sound, when we're dealing with sound waves. Here they are destructively interfering. But in these peaks or troughs, they are constructively interfering. So that's why we observe the waves here. But in this region, it seems, if you were to look at this region of the string, it would seem there's no wave on the string. However, if you look in this region, as indicated by the green arrow, in this region you will certainly see the string being displaced from the horizontal. Hence, we would observe the wave. Electrons, since they are also waves, they also obey this principle. Now, this idea of constructive and deconstructive interference can be made more concrete, in particular mathematically. Since electrons are waves, this means the regions that electrons can occupy must be where they constructively interfere. But what region will electrons interfere constructively? Well, waves have a period of 2 pi in general, especially sinusoidal waves. They have a period of 2 pi. That is, every 360 degrees they begin to repeat themselves. That is a standard, for instance, sine curve or cosine wave. Now, electrons will orbit. In other words, the allowed regions of electron orbits must have a circumference which is a multiple, an integer multiple of 2 pi. In other words, the circumference of that orbit must be a multiple of 2 pi. The circumference, which is 2 pi times the radius, this is the circumference. That circumference must be a multiple of the wavelength of that electron. Sorry, I'd like to repeat that. The allowed orbit for an electron must have a circumference whose magnitude is equal to an integer multiple of the wavelength. I'm going to change this. This should be lambda. There's a mistake here. This should not be, this should be lambda. The 2 pi should be a lambda. I will update that. Which means, mathematically, that's what that looks like. That is, the integer multiple of the wavelength must be equal to 2 pi r. That is the circumference. Hence, if we take lambda, remember lambda from the previous discussion, that is the lambda, the wavelength associated with the electron, is given by this. Now take this fact and plug it in here. What you obtain is this formula here. Notice this formula, of course, with a little bit of shuffling around, and that shuffling around, I leave it to you as an exercise. If you take this fact and you substitute it in there, and you just shuffle things around, you will obtain this formula. Notice this formula, it is exactly the postulate by Bohr. That is, momentum, angular momentum of an electron comes in integer multiples of h over 2 pi. By treating the electron as a wave, we rediscover Bohr's postulate. So it is this idea why Bohr's postulate works and it enables us to calculate the allowed orbits of an electron. So Now we have a complete picture as to why certain regions of an electron are allowed. It has to do with the fact that an electron has a wave nature, and its wave nature allows electrons to only exist where there is constructive interference. And with that, I will stop here. See you in the next one.